I'm Robert Neumann. I'm a security researcher at ForcePoint, working in the Special Investigations team, and I would like to share one of the recent investigations and about the title. So, the 4K theory. When you hear the 4K as a kind of a word, what is the main association you have? So usually it's television with ultra high definition, because that's something from the past couple of years. There is 8K, still 4K, something good, but that's just one thing. The second one is good old cache, because you are usually saying that it's 4000 or like 4K. And the third one is something kind of a retro thing called a 4K demo. So I'm not sure how old you are here, but this is something which goes back to probably the 80s or the 90s. And it was representing a very short piece of code doing very fancy graphics on computers. And thankfully, this is still not extinct, but a little bit more on that later. So a couple of questions before we proceed. How many of you can actually understand assembly code? Hands up. Don't be shy. Okay, that's reasonable. So how many you are actually still writing assembly code? That's more tricky. Hands up, because I know that you might be doing still shell codes, right? Okay, that was the tricky part. So it will be likely a bit high level, but I was trying to also include some assembly level stuff, mainly for you guys who are still coding. Okay, and how is it all connecting to the talk? So is it a present or the past? As you can see, that's a POS terminal, and it's a kind of a bad play with the words, but let's see. So there was a UDPOS discovery that was by us at ForcePoint early this year. That was basically a new piece of POS malware family. Wasn't really earth-shattering or anything what we haven't seen before. The novelty was, or one kind of novel feature, that it was using DNS for data extraction compared to other methods. DNS and data extraction over DNS is not really that new, but there weren't many POS families utilizing it before, and we only had a handful of samples of that. Then there was the pink eye story. It was almost at the same time. It was by Kroll security researchers. They were finding a small piece of POS malware. According to them, it was between 4 and 6 kilobytes in size. And the interesting bit there was that it was using a kind of clearing houses for storing all the stolen credit card data. And also, they were claiming that it was using the very famous double XOR encryption, as much as we can consider that as an encryption. And the pink eye story goes back to a little bit of the past. So when we were reading about the story, and that is a small piece and it's a POS, there were kind of small bells ringing. So it's very much looking like there is the old tiny POS / Abaddon POS malware resurfacing, or might be a new iteration of that, or just kind of ideas borrowed for that or whatever, but that was very, very similar. And last but not least, it's Joker Stash. Some of you might know the name, so it's a kind of famous site for selling and trading credit card data. And the owner, or maybe there are multiple owners, they are kind of proud of their work. And just recently, they were claiming that they were hacking into merchants directly, and they are responsible for a couple of recent breaches. Brian Krebs was having a very nice summary on them, and also kind of a fake Joker Stash site. So that is going to kind of add up at the end. About the investigation. So we were basically just starting to collect samples. We were not really expecting to have too many, because from the previous experience with UDPOS and other POS malware, it was usually just a handful of samples what someone can gather. We started to collect those samples very early this year, and as of today, we have more than 1,500 unique samples. Of course, they are falling down into a couple of different categories, but when unique, it's of course, it means that it's hash unique. The sample size is varying between 2 and 7 kilobytes, but it's, as the title was saying, it's mostly about 4 kilobytes. And the majority of them seemed to be downloaders. The real payloads are few and far in between. And as just to play with the numbers, I can say that the real payloads were probably less than 40 samples total. So that was a little bit suggesting that it might be a stage approach. First, about a couple of obfuscation techniques. I'm not going to tell kind of which part or which module had what techniques. I was more like combining all the techniques and collecting them here. So these might or might not be all used by the different samples. The kind of call push obfuscation is a very simplistic one. I will have a nice example for that and explaining there. Fake API calls, nothing new there, kind of having fake code, fake API names. The code is not being executed, the execution is jumping over all those fake API calls. Junky instructions, as having the usual NOP slats or any other fake instruction, as again, it's jumping, the execution is jumping over from them. Import by hash, once again, kind of an old feature or old technique. Changing equal resources, that's very easily done. The same about randomizing the VS version info. There are no real anti-debug or anti-virtual machine or sandbox tricks. Probably that was not needed. There is almost always a very simple encryption layer on top of the compiled executables, and it seems to be applied after compilation. I will explain later why. And in a couple of cases, there is some AV process names in the blacklist. So there is extensive black and white listing by these modules. The AV names are there not to make execution stop, but basically just to prevent those processes to be opened. And there is an example of the first kind of call push obfuscation. I know that it might be challenging to see. It's actually, if you are running or jumping the gun and loading the sample into IDEA Pro, this is what you get. That's kind of your entry point. What you can see on the screen, there is a load library, there is a get process address, and there is a create mutex. But basically, you cannot really see any parameters being passed or anything which is sensible. So that's the case when you are a little bit fast and you are using IDEA by default for everything. If you go back to a very nice old-fashioned hex editor, that's the same code. The ones who are reading, writing assembly can see that that's actually a E8, that's a call, that's the same entry point. Here you can see that there is the anti-DLL, there is the adduce privileges API, and there is a nice kind of old name for a mutex on the last line. So that's just an example of why it makes sense to use different tools for the same task. So the first component, the downloader, and I would kind of like to refer to it as a tiny loader, because that's also something from the past, and we are being almost sure that this is the same family or derivation from that one. The downloader is always having an additional encryption layer. You can imagine that as a kind of a short XOR decryption loop that's usually at the entry point or close to the entry point, and it's just decrypting the additional code. Nothing too complicated. It's very basic obfuscation technique, so you cannot really see the internal content by just using the hex editor. The downloader is supporting dual C2 IP addresses. Actually, there is a little of a laziness on the side of the developers, because most of the samples are only utilizing one. And even if you are using only one, they are having the same constants in the code. So they were not cleaning up the code to have a version where it's 2 IP addresses or have one. It's always flipping back and forth, but basically they are using 2 or 4 times the same constants. And that's a very easy and convenient way for them. The main purpose for the for the downloader is to retrieve a shellcode and execute it. I'm going to talk about that next later. The shellcode is also encrypted, same XOR-based encryption, nothing overcomplicated. And due to the shellcode and due to the structure of this, the downloader is capable of running any custom shellcode, what you would like to do, or execute a normal PE executable. There are suggestions that they might be using it for other operations than their own, but we've been dealing with one type of shellcodes during our investigation. About the C2 IP addresses, the IPs are usually lasting for a period of time. That means that a couple of months or some older IPs might be coming back. Whatever is changing, those are the ports. So if you are looking at samples in kind of in a timeline fashion, then we could see that ports are changing likely by 1 increment or by 2 increments, and those campaigns are kind of dying off every second day or every next week, and just a new one arriving with the same IP address but a new port. So a little bit about the shellcode. As said, the shellcode is being built up from multiple fractures. When I'm saying shellcode and when people are thinking of shellcode, you are thinking of something very short and very basic functionality, just a couple of hundred of bytes. This is slightly different here. So this is kind of the hex dump of sort of first level shellcode. As you can see, this is not that tiny. It's not clearly readable, but there are lots of API names. There are some interesting strings. What happens in reality is, if the downloader can connect to a C2 and the connection is established, it's sending data there and then trying to retrieve something. So when retrieving, it's only downloading like a couple of 100 bytes per each run, and then that's already a shellcode and some additional data. So like one piece of couple of 100 bytes is going to build up this whole piece by copying the rest of the content to a certain memory location and then giving back the signal that, yeah, I need another piece of this. This one is probably after like 6 or 7 pieces collected together. Once it was complete, the execution is being passed over to that. It's pretty much just resolving those API names and also having process blacklisting or process filtering. That can be shown a little bit in a more readable form here. So it's basically kind of easy to see a certain system process names, only using like 4 characters for those. And if those processes found, then those are being skipped. If the process is not on the kind of blacklist, then that's going to be flagged. The downloader and the shellcode has a certain way of interaction. So it's not like the downloader is passing over execution to the shellcode and then a shellcode does whatever it wants. The shellcode can also give back information to the downloader. So after the kind of process blacklisting, it was gathering all the process names on your computer, then passing that back to the C2 in a list. And if you are a nice victim, then you get something back as for the second part. So this is, once again, being built from fractures, and this is actually a full downloader shellcode. So the story is not ending here, because this is capable of downloading something, unless you are also receiving an additional IP address, a port, a file name, or an actual URL, it wouldn't do anything for you. So if you are not one of the targets they are looking for, the next shellcode after this, what you are getting back, is basically a nice sleep of a couple of minutes, then a nice sleep of a couple of hours, and then a nice sleep of a couple of hours, and it goes on. So it wouldn't really exit from memory, but it would be just waiting for another command, or maybe that they are trying to send you a different type of payload. So the next module is the Scout. It's having 2 types. They are both very easy pieces of code. And basically the type A is just collecting the running process name. So it's a small executable looking through all your process names and basically making a list of that. it's trying to open all the processes. If there is an error, there is a flag of E or F, like for fail. They were changing it sometimes for whatever reason. If it could be opened, then it's a no. And then it's building up a list of all the process names and the flags and sending back to another C2. So basically, it's a very easy mapping of your running processes. Type B is a little bit more complex, but just a little bit more, and it's more targeted. So Type B is also having a huge list of POS process names, and it's also doing some additional tricks, like getting the name of the PC and also doing a network map. That's actually using a simplistic net view for that, and also doing the same process walkthrough, but this time it's only looking for processes from the POS list. And that POS list is this. So to understand or put it into context, you have to know that there are 6 characters for comparing one process. So they were not really bothering to have the whole long process names here. Why would that be needed? They are only comparing like the first 6 characters of every process name. If you do the math, because actually I know the size of that, that means that that list contains over 300, actually 327 POS names. So that's a really an eye-opener, because in reality, if you are going for a new business, as if you are kind of buying a POS terminal and all the hardware and software related for that, you have one POS system running. There are no trial versions of this software, so it's not like if I'm asking you to collect me like the top 10 simplistic graphics editors on the net. You can easily kind of grab those, install those, check what process names they are using. Here, it's much more complex because you need to spend money and invest money, or you have to start mapping a lot of networks and looking for process names. So this alone indicates that whoever is behind these modules and these campaigns, they were not starting it today or the week before, but likely doing it for a couple of years or more. And then finally, the POS module itself, a little bit strangely, but maybe not that strange that it's not utilizing any encryption. Basically, if someone is reaching, or a PC is reaching this point, then they are almost very sure that they are a capable target. So that's likely a POS terminal. There is no analyst sitting in front of the PC. Most of the time, there is no AV installed or anything like that. Why would they be hiding anything in the binary? They could be applying the very same simplistic XOR. They decide not to do that. The main purpose of this module is what all the kind of old other POS malware were doing. It's tracking and collecting the track 1 and track 2 credit card data from memory and using them and sending those to the C2. The POS module can also kind of contain black and white lists, as seen before with the shellcode and with the Scout. Sometimes they have a short list of POS names, sometimes they have a longer list, sometimes they also have a blacklist for processes not to be opened, and sometimes they are kind of combining the two. It's always different. Having said that it's a basic memory scraper, there is still some minor maintenance going on the code level. I'm going to show an example for that. And it's actually a multi-threaded memory scanning. So whenever one process is found to be interesting, and it's either not on the blacklist or it's included in the whitelist, that's going to be opened and the new thread is going to be started and all the data is going to be scanned, whatever is accessible. There is the example for track 1 and track 2 data. So whoever was not dealing with POS probably never seen this. This is basically what goes through on the wire when you are using the old-fashioned magnetic stripe card payment. So as you can see, this is kind of plain text, no encryption, nothing else. All the vital data needed to complete another transaction is there. So if you can steal that, you can kind of clone a card or use that data for other transactions. And this is what's actually being extracted from running the POS module before encryption. The POS module is using a basic XOR before sending that over to the C2, but that's just likely for the DLP and other systems, so they are not flagging the traffic as credit card data. As you can see, I wasn't using the very same card number, but basically it's a track2 data, and there is a process name listed what was my test POS executable, which was nothing sort of fancy. It was actually a notepad, and I was pasting that just for memory scraping purposes. And then one bit of evolution from the POS part. So on the left, you can see that this is part of the memory scanning procedure. There is a memory read. After the memory read, there are certain checks, and on the bottom, you can see byte compares. Those are basically looking for digits. So it's likely 3, 4, 5, 6. Those are the usual digits for your credit card. That's the kind of the starting numbers. There is a whole long of parsing code beyond that point. So looking for all the specific and special characters from the previous slide and validating it all. But this is where there was actually some improvement. So on the right, you can see the very same code, except that there are 5 more conditions. And actually, it seems that by just reading memory, either it's running on an exception sometimes, or the timing is key, because on the old sample, on the left one, that was from like January or February this year, they were almost reading like 400 kilobytes, and then having 1 millisecond of sleep. That's not really a long one. On the right, they do that a lot more frequently. So likely they are testing this on a lot of systems, and they are trying to fine-tune so it's not resulting in an exception, it's not having any memory reading problems or anything like that. Beside this minor change, the right-hand side sample is very recent. It was from September, and the parsing code and everything else is the same. So basically what the usual operational workflow for them. On the left, we can see that there is the scout. That would be mapping all the data and all the processes, what they can. They were not converting that or compiling that into x64. There was no reason. The key was always static in that case for all the samples we had from this year. The port number was those 2. That was also not really changing, and it's only a very few IP addresses they are using for sending back the process data. So in their infrastructure, they are trying to distinguish which data goes to where. There is a kind of an overlap, but they are trying to distinguish the different functions. Then, of course, if there is a good candidate, there is going to be a downloader. The downloader, there is no encryption. It's actually the brute forcing of themselves. So the top layer encryption is not having any key stored. There is no need. It's just doing a D-word brute force, which is very fast on current CPUs, and then it can decrypt itself. It's using many different port numbers. As I was stating, that the port number is frequently changing, and it's using almost like 10 different IP addresses, so that was from this year. And then finally, you have the POS. It's having also a key for the encryption for data sending back to the C2. It's multi-platform. It's always using that very port number, and it's also only connecting to a very few ones. And then if you get the credit card data, then they do the cache out, and the whole cycle goes back to the beginning. As you could see from all the POS process names, it's likely a lot of cycles, likely hundreds or more of evolution, and constantly looking for new possible targets, constantly mapping PCs, and having a good understanding of who is a good candidate and who is not. So what the problem is here? First, there is the software side of things, and that's partly starting with POS Ready 2009 and POS Ready 7. So those are Microsoft platform names. You can probably guess that POS Ready 2009 is XP based. What a surprise. POS Ready 7 is Windows 7 based. One problem is that people are still using the older POS platform, and we pretty much know how secure XP is. The other is that no matter what you use, soon they are going to reach end of life. They are already on the extended support, and the dates are next April for POS Ready 2009, and sometimes October in 2021 for the Windows 7 based one. The other problem is that what we could learn from past experience, that often there are remote access applications being pre-installed on POS terminals. So that's not really a surprise. Imagine your average IT administrator, they don't want to kind of walk down to all the POS terminals, updating whatever software is running on them, especially kind of imagine something big in the United States, which is nationwide. Of course, they have multiple IT stuff, but doing that from a central location and easily and conveniently updating software, that's always good. The problem is sometimes they, as they are IT people, sometimes they forget to change default passwords or use the same password for the whole countrywide stuff, and that's just providing an additional attack surface. The track 1.2 data lacking any encryption, you could see that it's kind of plain text. There is nothing more there. The new track 3, which is kind of the EMV base, what I'm going to talk about later, that's using 3DES, RSA, and AES. So they were thinking ahead of the problem already years back, but this is what it is. We are dealing with legacy systems here. And for last, that's additional third-party applications might be running on the POS. So in a couple of instances, there might be an SQL server or an equivalent, and imagine that if it's storing historical data, and that's loaded into the memory, then you are not just dealing with actual transactions being stolen, but also something from all those historical data if the post scraper is able to grab the data from the memory. And then we are switching over to the hardware side of the problem. So it's the old debate, magnetic stripe vs EMV, which is the chip and pin terminals. Actually, EMV is not a new standard, but something old. It was already standardized originally in 1993 and 4, so it's almost about 25 years ago, and they were already thinking of encryption back then, at least the basics. And by the way, it was standing for Europay, MasterCard, and Visa. I'm not sure if many still remember what Europay was, but likely that's also something a blast from the past. Another thing which might be a problem, but the liability shift. So banks a little bit got fed up with all these, that people were easily stealing credit card data. And of course, they are the ones trying to insure the money and trying to be responsible for whatever was stolen. People going to the bank, hey, I got any kind of card fraud, please give me my money back, because I can sort of prove that it was stolen from me. So you can see and understand that they were fed up pretty easily about that. So they wanted to change that, and so they did. In the EU, it was 2005 and the 1st of January when they were having the new laws for this. In the US, it took an additional 10 years. It was just 3 years ago. So at that point, they were kind of moving all the responsibility from bank to merchant, and the merchant is being responsible if there is any kind of non-EMV transaction happening and there is a fraud. Also, there's a human factor. We are lazy people, I can say that. We like to easily just swipe the card. We don't want to enter a PIN code, especially that's true in the US. Sorry, guys. One possible solution here would be that they are switching over to contactless payment, because that's also kind of a convenient way, but that is only happening in the past years, and still switching over to anything still involves money, as they have to replace the terminals and the software, and if you think of nationwide, that can be a lot of money. A couple of anomalies before I am closing it up. So when we were having a look at all those samples and we were doing the investigation, something kind of stood out, that they were very quickly closing down the ports and changing to new campaigns. But sometimes you are lucky, and there are very old IPs and ports being kept open. So I wouldn't say it's really a failed OPSEC. It's just kind of a bit of a laziness, or maybe they were overloaded with all the different targets and the work, but that sometimes helps you to actually have a living connection and retrieving the shellcode. Also, we could see a very similar downloader actually downloading what was an XMRig miner. So that there are a couple of differences. It was using scheduled task for persistency, but the assembly code loader was very similar, and sometimes they were using PL compact, which is a very basic executable packer. That seems to be a spin-off. I wouldn't say that these are the same people, but actually crypto mining and cryptocurrencies were a big thing in the past couple of years, so it wouldn't be senseless to say that they were extending their activities. And for the last, that was kind of the strangest one, and that's the server IP range. So whoever was working with the server ransomware before might know that the server is looking up a very big list of C-class IPs for any kind of C2 communication, or the possibility of that. And that means if you try to hunt for data, and your actual IPs from this POS campaign are falling into that range, you run into an awfully lot of server kind of samples, and that's just making your investigation even harder. As for a conclusion, so it's a 4 kilobytes, usually assembly-based application, purpose-built. It's very easy to borrow ideas from such small executable. You are not dealing with any kind of library and high-level language code and library stuff. It's just the pure user code. It's also very easy, so you can imagine if I wanted to rebuild the same on a source level, it's 4 kilobytes, it's not taking more than a couple of days stop. And I am rebuilding, I have a source code, I do whatever I want with that. Also, it's true that you don't really need massive amount of code to implement basic functionality, kind of purpose-built for just doing a very basic thing. The exploitation of POS systems is unfortunately still happening due to the reasons I was just discussing with you. All the hardware and the software issues combined together, making it possible. And there is a problem with software delivery and update chains. So it seems to be reasonable that some teams are also utilizing hacking and either getting to a computer which is a software delivery chain, which is taking part in the software delivery chain, and using that to spread all the downloaders to all the POS terminals, or they are hacking the remote access tools already pre-installed and using credentials to get into companies that way, and that's where we can connect back to the Joker stash statement that likely stealing that many data on that level is not possible on a different way. A couple of thanks to guys helping me and a couple of organizations I was using the graphs. I wasn't talking about the charts because it would just take time. I'm going to share the slides, and I'm also going to share IOCs in our upcoming blog post, all the samples, the C2s, and mutexes and whatever we were gathering. Questions? Then thank you very much for your time. I am here if you want to have questions in person or by email at a later point. Thank you, guys.